Alrighty, we're going to conclude our work with logs as we talk about solving equations using logarithms. In this video, we're going to talk about a lot of different situations here, and we will conclude with some word problems. Our first situation that we're faced with is an exponential equation where finding the same base is impossible. Remember that when you were solving exponential equations, if you could rewrite terms so that they had the same base, you could then equate the exponents together. But in these types of questions, that's not going to be possible. What we're going to do is we're going to take the log of both sides, simplify, and then simply evaluate it. And you'll see in questions like these, it'll ask you to round. In this case, we're being asked to round to the nearest hundredth. Our first example here is 7 to the power of x is equal to 400. We can clearly see that 400 is not like a multiple of 7. You can't do 7 to the power of something is 400. So we're just going to take the log of both sides. Now what this allows me to do is it allows me to pull my exponent of x on the 7 and bring it out front. So I now have x log 7 is equal to log 400. Log 7 is a number. I could type that in my calculator and get a number. Just like log 400, that's also a number. And so I can get my final answer for x by saying, well, what is log 400 divided by log of 7? If I were to stop here, this would be my exact value. So if you were being asked to find the exact value, this is it. You would stop. In this question, we have been asked to round, so this is the point where I'm going to type it into my calculator. Log 400 divided by log 7 is about 3.08. Okay. Let's look at question B here. 7 times 1.06 to the power of x is equal to 5.2. I want to get it looking like our first question here, where I just have one term with an x and nothing else happening to it. And so here what I'm going to start by doing is actually dividing both sides by 7, leaving me with 1.06 to the power of x is 5.2 divided by 7. I'm not going to put that into a decimal until the very end because I want to keep my math as precise as possible until I type it into my calculator once. Now I take the log of both sides, and I bring that exponent of x out front. So I have x log 1.06 is log of 5.2 divided by 7. And so my x is going to be equal to log of 5.2 divided by 7, all divided by log of 1.06. Again, this would be the exact answer if you were asked for the exact answer. But here we're being asked to find an approximation and round to the nearest hundredth, so I type it in my calculator and I get negative 5.1. Okay, a bit more of a complicated problem here. 4 to the power of 3x plus 2 is equal to 3 to the power of x minus 1. Clearly, they don't have the same base, a 4 and a 3, so we take a log. Log of 4 to the power of 3x plus 2 is equal to log 3 to the power of x minus 1. I bring those exponents out front, making it a whole lot easier. 3x plus 2 times log to the 4 is equal to x minus 1 times log of 3. I'm going to distribute these brackets out. Okay, so I will have a 3x log of 4 plus 2 log of 4 is equal to x log of 3 minus log of 3. I'm going to rearrange so that all my terms with x's are on one side. So I'm going to bring this one over to the left. So I have a 3x log 4 take away x log 3 is equal to negative log 3 minus 2 log 4. Of my two terms on the left, I can factor out an x, leaving me with 3 log 4 minus log 3 is equal to negative log 3 minus 2 log 4. And now I'm going to divide everything by this so that I isolate my x. X is equal to negative log 3 minus 2 log 4, all divided by 3 log 4 minus log 3. Again, this is our exact answer. If this is what we were being asked for, you would leave it like this. I know it looks like it's a lot, but this is the most precise answer. Okay, but here we're being asked to type it into our calculator. And this is going to equal approximately negative 1.26. Okay, lots of different work here that's happening, but we're being true to our log laws. And at the end of the day, it's a little bit mindless work. You just sort of have to respect the rules. Now, a different situation that you might be faced with here is when you are starting from a logarithmic equation. So like, just take a look at our first example here. I have log of something is equal to 1. There is no one strategy that we can use. Okay, so there's a lot of different things that we have to try. We can try simplifying using log laws. Maybe you want to rewrite it as an exponential equation or a logarithmic expression. You might need to factor, you might need to use the quadratic formula. Just be creative. Now note that extraneous roots are possible. Extraneous roots are roots that cannot exist. They cannot exist. It's not possible. The thing to remember is that log is undefined for a negative x. So if we ever get an answer that's negative, we have to disregard it. Okay, sorry, not negative answers. We have to pay attention, okay, to our original question and see, are we inputting any negatives? And you'll see what I mean by that when we do an example later on here. Okay, so let's do our first one. Find all solutions for each logarithmic equation. Here I'm being asked log of x minus 5 is equal to 1. Remember that there's an invisible base 10 here, and the way that we rewrite this as an exponential equation would look like this. 10 to the power of 1 is x minus 5. This is pretty easy to solve. This is like a regular question. 10 to the 1 is just 10. I'm going to add 5. 15 is x. Okay, that was pretty straightforward. Similar style here. Log base 5 of 3x minus 4 is equal to 3. Let's rewrite it as an exponential equation. 5 to the power of 3 is 3x minus 4. 5 to the power of 3 is 125, is equal to 3x minus 4. I move the 4 to the other side, I get 129 is equal to 3x, and when I divide both sides by 3, I get that 43 is equal to x. How lovely. All right, question C. Log base 6 of x plus log base 6 of x plus 1 is equal to 1. These two logs have the same base and they're being added. So what I'm going to do is I'm going to combine them into 1 using that multiplication property. So this is going to be log base 6 of x times x plus 1 is all equal to 1. This makes it easy for me now to rewrite this as an exponential equation. So I know that 6 to the power of 1 is going to be x times x plus 1, or just 6. I'm going to expand here. This will be an x squared plus x. And if I move my 6 over, not equals negative 6, just negative 6, this is a quadratic, right? I can solve this by factoring. I'm looking for two numbers that add to 1 and multiply to -6, and those two numbers are x plus 3 and x minus 2. So I set them both equal to 0. -3 is x, or +2 is x. Now here's where we need to check, and I'm going to go back and I'm going to check all of my possible answers here, okay, with our extraneous roots. So remember we said extraneous roots, you have to ask yourself, are we inputting any negatives? Here, in example A, my answer was 15. If I substitute 15 in for x in my original question, does x minus 5 become negative? No. 15 minus 5 is 10. This remains positive, so this is not an extraneous root. This is totally possible. For question B, my answer was 43. If I put 43 in here, do I get a negative number? 43 times 3 is 129, minus 4 is 125. That is still a positive number, so we are good. It is not extraneous. Here, however, we are going to have an extraneous root. Just look. One of our answers was -3. This is a negative number. If I put it in here, log of x, I can't. I can't take log of a negative number. Even if I tried it in here, this whole bracket would become negative. So this is an example of an extraneous root. So we throw it out. Is our other root good? It's +2. Works in here, works in here. This one counts. So that is our only possible answer. Okay? And if you need to write it down, okay, this is an extraneous root because log base 6 of -3 is undefined. Okay, so x is equal to -3 is not a possible answer. Let's look at question D. Log of x plus 5 plus log of x plus 2 is equal to log to the power of 4. What we can do here is this new technique that I'll show you in one step, okay? First, what I'm going to do is I'm going to combine my left side so it's all one log, okay? I'm using my product law here. This will be log of x plus 5 times x plus 2, all equal to log of 4. Now, something that you haven't seen before, one new strategy, is if you have logs with the same base that are equal to one another, that must mean that this stuff in the middle is also equal to one another. So what we're able to do is we're able to just jump to x plus 5 times x plus 2 is equal to 4. Okay, we're allowed to do that because they have the same base and we are being told they're equal to one another. I'm going to expand my brackets on the left-hand side to give me an x squared plus 5x plus 2x plus 10 is 4. Combine my like terms and move my 4 over to get a 6 is equal to 0. I'm going to go ahead and factor this. Two numbers that add to 7 multiply to 6 are 6 and 1. And so I'm going to set these each equal to 0 to get my two possible answers. Now I need to go back through and check, are either of these extraneous roots? X is equal to -6. If I put -6 in this first bracket here, I'm going to have a negative. just like here, it's going to be negative. So this is an extraneous root. Right? Log of -6 plus 5 is log of -1, which is impossible. I'll check my -1. If I put -1 in my first bracket, I will still end up with a positive. And if I put -1 in my second bracket, I will also still end up with a positive. So -1 is a possible answer, and in fact, it's going to be our only answer here. All right, one last problem. Log of x minus 1, take away 1, is equal to negative log of x plus 2. I'm going to do some rearranging, so my variables are on the left-hand side. And my constants are on the other side. I'm going to combine the two terms on the left-hand side using the product property or product law so that I only have one log. And the strategy that I'm going to use here is that I can rewrite this as an exponential equation, right? There's an invisible base 10 that's at play here. So I know that 10 to the power of 1 is going to be equal to the stuff in the middle. And 10 to the power of 1 is just 10. So I can say, well, x minus 1, x plus 2 is 10. I'm going to expand this. X squared minus x plus 2x minus 2 is 10. Then I'll combine my like terms. X squared plus x, and then this will be negative 12 is equal to 0. I'll factor. This will be x plus 4x minus 3. And so now we check our solutions. I get that x is equal to negative 4, or x is equal to positive 3. Are either of these extraneous roots? We check negative 4 first. Negative 4, yep, that's extraneous because x minus 1 would still then be negative. So this is extraneous. What about positive 3? Positive 3 take away 1 will remain positive. Positive 3 plus 2 will also remain positive. So this one's good. X equal to 3 is your only solution. Okay, let's talk about some word problems now. There are sort of two styles of word problems that you are going to be given. And within those, it could either be increasing or decreasing. The first style are what we call exponential growth and decay. So it's growing, it's multiplying by itself. It's, I tell a rumor to two people who then tell two people who then tell two people, that sort of thing. And there's a lot of different letters here to indicate various things that are happening, okay? The first that you need to know about is P. P is your starting value. It's also called your principal. Okay, how much are you starting at? A, I like to think of as your final amount. Where do you want to end at? So for example, a question could be something like, I put $1,000 in a bank account with a certain interest rate. I want it to end up at $1,200. The start there would be 1,000. The end would be 1,200. Okay, A is always sort of in the future as compared to P. N, up top here, our exponent, is the number of repeating periods. And it's often our unknown. So back to that example question of, I put $1,000 in a bank account, how many years is it going to take for that to grow to 1,200? That's what we're looking to find out, okay? It's an amount of time typically. And then the last variable that we need to know about is I. I is that interest rate, okay? Or it is, more generally, it is a rate of increasing or decreasing as a decimal. Very oftentimes it's going to be given to you as a percentage. You use a plus if it's talking about growth. So I'm going from $1,000 to $1,200. Or you use a minus sign in your formula if it is decaying. So for example, I bought a car worth $40,000. It's now worth $20,000. It's depreciating at a rate of blah, blah, blah. How long did it take? That sort of thing. Something's where it starts and then it's slowly decreasing. Plus for growth, minus for decay. Now there are two more formulas to be aware of, our half-life and our doubling time. Okay, a lot of the values remain the same here in terms of the structure of the formula. Okay, we have our AO as an original amount. What are you starting at? And then AL, I don't know why it's called AL, but it's like the amount left. It's the amount in the future. T, similar to N, is the amount of time it takes. We're often looking to find T. N, at the bottom here, is your half-life or doubling period. And this is going to be given to you. Okay, half-life is used for things like, think back to lesson 8.2 where I had that word problem and I was using the bug spray to help deal with my gnats in my indoor plants. A half-life would be something where it's like, hey, every time you spray, it gets cut in half. It's often used for decay for like chemical compounds and stuff. So it's like the half-life, so how long it takes for it to be cut in half is this amount of time. A doubling period would be sort of the opposite. It's how long it takes for the amount to double. So that would be something like a bunny population is being studied and we know that the doubling time is 5 years. So it takes 5 years for the bunny population to double. And you would be needing to figure something out based on how many bunnies we started with, how many bunnies we've ended with, how much time has elapsed between the two. Now what you'll notice here is that we've been provided with our brackets. Half-life, of course, corresponds with the half, and 2 would correspond with the doubling time. Okay, so if you're dealing with a half-life problem, you would use the 2. If you're dealing with a doubling time problem where something's doubling, you would use the formula with a 2 in it. Okay? Let's do 2 examples where we have to select the correct formula and create our own equation, which we can then ultimately solve. A house is purchased for $200,000. The value of the house increases 5% per year. How many years does it take for the house value to increase by $50,000? Okay, we've got a lot of information provided to us here. Let's break it down. First things first, I recognize that I am not dealing with a half-life or doubling time because nowhere in the question did it say anything about a half-life or a doubling period. So these formulas are out. It is asking me to increase, and so I am going to be selecting the formula with exponential growth. A is P 1 plus I to the power of n. P is our principal value. It's our starting amount, which in this case is 200,000. And we need to know that how long it's going to take for it to increase by 50 grand. The final amount then is going to be $250,000. Okay, we don't just want to rate 50, we want to rate 250 because that's the new value. We've been told the I is 5%, so I'm going to write it as a decimal, 0.05, and we need to find our end value. So I'm going to set up my equation here. 250,000 is equal to 200,000 times 1 plus 0.05 to the power of n. I'm going to rearrange, divide both sides by 200,000. And simplify my bracket here to be 1.05 to the power of n. I'll simplify this fraction. 250,000 divided by 200,000 is 1.25. 1.05 to the power of n. Okay, we've taken this as far as we possibly can, and now we need to apply our log. We cannot solve this using exponential or following an exponential style because the bases are not the same. So we take the log of both sides. And this allows me to bring my n value out front. I can rearrange and divide both sides by log of 1.05. In order to find my n value. And typing this in the calculator, I get about 4.6 is equal to n. And because this is a word problem, I will conclude with a therefore statement. So I'm going to say, therefore, the house value will increase by $50,000 in 4.6 years. All right, our second and last example for today. A radioactive substance has a half-life of 8.2 days. How long will it take for an amount to reach 25% of the original? The question literally says half-life in it, so I know I'm working with the half-life formula. AL is equal to AO of 1 over 2 to the power of T over N. I need to figure out what all of these things are. The original amount that we're starting with is going to be 100. As in 100%. We're starting with 100%. Or just 1. Because the amount left that we're looking for is 25. Or 0.25. N, you'll recall, is the half-life. And we've been told here it has a half-life of 8.2 days, so N is 8.2. We're trying to figure out how long it takes to get there, so our T is unknown. I'll substitute this into my equation here. 8L is 0.25 times, I could write 1. I don't need to write 1 though. 1 over 2 to the power of t over 8.2. I can immediately now jump to taking the log of both sides. Which allows me to bring my exponent down in front. Okay, I'm going to divide both sides by log of 0.5. And I'm just switching to a decimal here because it's easier to write. Log of 0.25 divided by log of 0.5 is actually just 2. So 2 is t over 8.2. I multiply both sides by 8.2 to get 16.4 is equal to t. And so I can conclude with the therefore statement. Therefore, it takes 16.4 days to reduce to 25% of the original. With word problems, it really just matters that you are identifying the information you have, making sure you select the right formula, and then eventually you're going to apply your knowledge of log laws in order to solve. Okay, great work, everybody.